Hello, my name is Cameron Courtwright. I am an RJG business development consultant trainer. Um, get the opportunity to do a lot of consulting with companies on product launches and different activities around problem solving and stuff. And then, of course, I always have the opportunity to train other technical people, which is always a passion for me. Today, we're going to talk about optimizing the tooling tryout process. Where this process starts from the presentation perspective is really as it relates back to simulation. But from a standpoint of the overall optimization process, whether you're doing simulation or whether you're actually going to do risk analysis on your process, we could actually move back and start back to there. The perspective is that you have a program manager in most cases or a product engineer that comes to you and they want you to help them launch the product. Sometimes they demand specific things and they have goals and objectives that they want to meet. The challenge with those goals and objectives, those aren't always reproducible, if you know what I mean, from a manufacturing perspective. So what we want to do is we want to hit on some highlights on how you make this is reproducible in the manufacturing process as possible, okay? So we have this project engineer, her name is Lisa. She's gotten some process simulations done, and now she has this data, okay? She's done some risk analysis. She understands her machines and the different work cells that she wants to run in, which means that she has a group of machines, but all those machines have different parameters, and she's kind of came to a common denominator from a standpoint of looking at screw size, barrel, clamp tonnage, the types of cavitation that she wants, and really she's made her decision that she wants to run a 4-cavity tool. All right. Now, traditionally, we could take that process, build a tool, go through that, have the best tool in the world, and now we got to run it in all 4 of those machines in her group. And so what she's done is she's actually taken the opportunity to do a little simulation and bring it in from that standpoint. The challenge is we have a technician on the floor, and this happens many times, is that technician has this data, but they really don't know how to use it. As it says, how do I use this information to develop a machine setup? I've got some fill time data, some pressure scales, tonnage graphs, short shot pictures, and what do I ultimately want to gain out of this thing? Well, the bottom line is the program manager or the project engineer, they know what they want, right? And we need these things to be successful, whether I'm molding a part in a captive operation or in a custom operation. So they want to understand what their product levels are, their quoted cycle times, those types of things. The problem is with this big, massive work cell of machines, Elmer's standing back and he's going, how do I use this data, all right? So when we look at this from this perspective, even if I have a simulation or I spent the time to do a good risk analysis of this process, there's some things that I know, and then there's some things that I don't know. Obviously, at this point, I got a part, and the project manager has the plan for that part. Chances are they have the material. Maybe it's a material that they've ran before, or that you've ran before, so you have some familiarity with it. But then, in general, I got to know how that shape of that part's going to react in the process and how I can develop a process to get there. Okay. So we have a simulation process that happens, and of course we have Norbert, and he knows everything there is to know about the machine. Actually, he went out to Elmer and he got all the OEM specifications, and he knows he's going to run it in this machine, and this machine is really the least common denominator for the entire process. He knows what his limitations are. He knows what he can do. He knows how fast he can fill the mold, and he gives that information back to Norbert. Okay? So these are real machine limits. All right? So I'm already, at this standpoint, developing a process from the machine perspective. I know what the part is. I know what the materials is. I know what I want to do with the material. I've fed that back into a simulation or a risk analysis, and now I know the machine limitations. The end result is I want to have something that's tangible that I can measure, that I can put back out to the floor so that the technical staff can actually take the results and put it into the machines. Now, let's face it, not every technical person on the floor has the same level of knowledge. We'd like to think that everybody is completely data-driven around their process development, but we know that's probably not the case. Doesn't mean that they don't know how to do their job. It just means that they need what they need to build a process effectively. Norbert will do a good job. He'll build a process in simulation as it relates to the shape, but somehow I got to come back and I got to validate that and I got to make it useful. So in many cases, I'll get a bunch of these outputs that come out of the process simulation. Ultimately, it's somebody's responsibility to take that information and to make it more efficient. What I would like to do is I would like to have a tool that I really take through the conditioning process or the trialing process and maybe only have to run 1 or 2 samples, okay? Normal samples that we see ran out in manufacturing for a new part may be as high as 5 or 6 samples, sometimes 4. 3 is pretty rare, but the objective is to get this to 2, okay? And some of us sitting around the audience, we might know what some of these things are and how to input them, but my technicians aren't as savvy when it comes to looking at simulation, so I got to bring this information all to them. Some of the simulation outputs for scientific molding really relate around temperatures, water temperature used in the simulation, linear speeds, shot size, hold pressures, hold times, and all these things which I can relate right back to the process. At the end of the day, I want to validate what happened in the process or my risk analysis to what is actually happening on the manufacturing floor. And that's really where the rubber meets the road in this overall process. If I can do this in a timely fashion, I can actually take time and effort out of the overall process. So as you can see here, here's some of the correlations. Melt temperature, linear speed from the screw area, which delivers me fill time, hold pressure, gate seal, and wall freeze. Those are some of the items that I have. Cooling timers, mold clamps, so all these things can lead me right back to what I need to put in the process. Now, my technicians may not understand this, but that's where I kind of got to get them to. So what I want to do is the first step in this overall process, like I said, whether I'm doing a risk analysis on my process or I have the simulation data, I need to translate and transport this information to the production floor. And I need to make it a very systematic approach using the 4 plastics variables. So as you can see here, Lisa is helping Elmer. I can convert these process outputs into useful machine setup information. She's a Master Molder 1 grad, so she's been given the understanding and the technology to convert this information. And now Elmer actually has a setup that he can use based on the 4 plastics variables. So obviously now he can actually use this information, and he goes to the machine and starts to put the process in. Immediately it's saving him some time and effort. Now, he has to have a little confidence in what he's being given, and sometimes that's the challenge when we talk about simulations, but validating that and verifying it is where it becomes important. So here's the converted machine setups, and to some of you this may look very familiar because these are some of the elements that you actually put in the machine. So, for example, barrel temperatures, screw RPMs in percentage on this particular machine, back pressures, actual melt temperatures, which is an output, shot size, and things like that. Pack pressures, hold pressures, and then of course cooling time, cycle time. So these are all inputs that you can use and the outputs that go along with those, such as fill time, cycle time, and things. So at this point, what I've done is I've converted this simulation data or my risk analysis data back to the converted machine setup. Now I'm ready to go to the machine. Before I actually go out and start running the machine, I still want to do some verification. And those verifications are really common to people in the systematic world. First of all, I'm going to do some functionality. I'm going to complete a robust tool trial and a functionality test. All this stuff in general can be completed in a matter of 3 to 4 hours, depending upon your cycle time. These are the questions that have to be answered before I start this process, though. Is the correct material in the machine? Do I have a material data sheet? Because I want my technical staff to understand what type of material they're running, where to set their heats, and where to get some of their information. Yes, that was already provided by the simulation process in the risk analysis, but now I want to bring it to the floor and have it there and it's useful. Is this material in the proper condition? As you notice, I put up there, do I dry polypropylene? Well, maybe some people aren't drying polypropylene, but there are a lot of people in the industry today conditioning their polypropylene to a specific temperature. It's not necessarily drying, but I need to know that I'm bringing that material in and I'm putting it in the proper condition. Is the tool set up correctly? Is it safely clamped to the machine? Is the water installed correctly? Are the correct knockouts installed and things like that? Once I've done these functionality checks, then I want to obviously understand, does the mold open and close? Does it do some other things? Do the ejectors work? And this is really the fundamental stuff of understanding the functionality of the mold. So once I've developed the process and I've got this information and I've translated it, at this point in time I might actually do some cavity balance studies and some various things that go along with a robust setup, which we teach in our systematic courses. So Elmer's went through that process. Now the material's correct, the tool's verified, and he's initially done things like cavity balance verification, linear speed checks on the machine, and those types of items. Now he has confidence that he can come back and match what has been put into the process. So he takes his setup that was created and actually translates it to the machine, transports it to the machine based on the information that he was provided by Lisa. Now he has a setup that he should be able to run and verify. I guess from this standpoint, what I want you to understand is not only are you verifying the process, you're actually calculating and figuring out how accurate your predictions were. As you can imagine, when you're doing a mold flow is still a prediction. Obviously, we want that prediction to be as high of a percentage as accuracy as possible, and the person that's going to validate that is obviously the technical staff. So I verify my machine setup information, and like I said, no matter how you slice it, a process simulation is a prediction that must be verified. Okay, so now what I'm going to do is I'm going to go through the verification process. So Elmer, he's going through the verification process, and for some reason, his fill time doesn't match. He needs to have some guidance and some understanding. So as you can see, this is a team event through the whole process, and what he wants to understand is which lever do I pull? And as you can see the little illustration up there, sometimes it's very difficult to tell which lever to pull. The reality is you did the simulation, you did your analysis based on real machine data, and now you should be able to predict what type of adjustments you need to make it correct. Lisa, who translated the information, comes back to Elmer and says, hey, let's verify the fill-only part before we adjust the transfer and velocity. Notice she's not saying anything about temperature. She's not saying anything about back pressures like Elmer's saying. I mean, she's coming back to a very pointed, systematic approach to address this situation. And then she asks a very important question is, what is the peak pressure at transfer? Now, if they modeled it appropriately and they had all the appropriate pressure drop information coming off the machine, she should be able to ask Elmer that question and get some pretty good information. This is where the verification step comes in. What she's actually doing is, okay, your fill time is incorrect. I knew I had a peak transfer pressure that I was trying to hit. What is that actually now? And so she's verifying the information that she originally had, okay? When we look at this, how this actually reduces the time to get back to a usable part is from the fact of, now that I've verified that process, I put it in and I've optimized it from a standpoint of the simulation. Pretty much at this point, if my product quality falls in line, I can run my sample at the targeted cycle times and my targeted outputs, and I should be able to produce a good product, okay? But the thing about process simulation is it always requires a feedback loop, and this is probably the biggest thing that gets overlooked in process simulation, is the fact that where's the communication between the technicians on the floor and the actual person doing the simulation and the program managers. Norbert says, hey, as I went through this whole process, everything that was in green were things that I achieved and were accurate to the process. That made the process extremely more efficient, but the things that are in red and yellow fell out of the process range that I was actually trying to achieve. From looking at this, you can see that these things that fell out, such as clamp force, which they missed the average cavity pressure in the part area, and the second thing, which is shot size, which was missed because of the nozzle or the barrel calculation, could be somewhat critical to the overall process. He feeds that information back to the person doing the simulation. They can go back and they can look at the data. It says, Elmer, we should look at these parameters so we can improve our process. Maybe we can verify further our machine information and mold with mold instrumentation. So they're feeding that back. So they're actually, as they're going through it, they're continuously improving the process, making it faster and faster. Okay. The fourth step is build a universal setup sheet for final documentation. That universal setup sheet that you're going to build, you're actually going to take that off the machine controller, and those other 4 machines that we talked about running in, now I'm going to convert those setups into plastic parameters. And those 4 plastics variables, I'm going to use those as a guide to lead me into processing in each of those other machines. Now, keep in mind, I've cut a process off of a simulation. I've verified that process. Now I'm running within my windows. I found the areas where I had deficiencies in my simulation data and found out that that was really somewhat machine related, and also some cavity pressures, and now I've finalized that, and I can actually come back and build a nice solid decoupled tube process sheet utilizing a universal setup. Once I have that universal setup, I can take this information and I can duplicate it in my other machines because I understand what their screw sizes are, I understand what the clamp size is, I have all the variables I need to match up with this, okay? So really systematic molding approaches. The instrumented process requires both a template and a universal setup. When we were talking about this process, we were actually talking about a decoupled tube process, which is all based around machine parameters, okay? But we can also have an instrumented process which requires both, not only a universal setup sheet, but a template that I can come back and match to. That universal setup sheet and that template are my guides. Really, the template ends up being the fingerprint of the process that I can take from machine to machine and match it. Some of you out in the audience I've actually worked with on cavity pressure details around building templates and things, and you guys are having some pretty good luck with those templates right now, duplicating processes. So if I'm going to run an instrumented process, I need to focus on having both a good template and a universal setup derived from the data that I transported to the floor. So if instrumentation is being utilized, focus on a development of a solid template approach after the process has been stabilized. This will help everyone be able to duplicate the process more effectively. So ultimately, this is an instrumented approach, okay? Steps involved in optimizing the tool tryout process translate translate and transport the simulation back to the floor, okay? I want to complete a robust tool tryout, which is going to include all the things that we would normally do centered around cavity imbalance, velocity linearity, rheology, some machine testing to get me to the next level. And then I want to develop a process approach using the translated simulation data or my risk analysis data that doesn't include the simulation. I want to build that universal setup sheet and that final documentation so that no matter what happens, my technical staff can take that from machine to machine to machine. Now, obviously, your technical staff has to have a little bit of insight into machine sizing, screw and barrel sizing, intensification ratio, and things, but that's definitely something that can be taught, okay? This is a team effort and has a huge payback potential. I can give you an example. We just actually finished doing a launch project with a team in Georgia where we worked hand in hand with them and not only did the full-blown simulation, actually with 2 simulation softwares, but we did the simulation, we validated the tool design, we came back and replicated that process using this similar approach. This company normally would have sampled their tools 5 to 6 times, and that was really common for them. We were actually able to take that sample activity by using these principles, educating their technical staff, bringing their engineers up to a level that they could use that data, and we reduced that actually to 2 trials. The first trial, we weren't successful on developing an instrumented process because the tool wasn't functional and the ejectors actually hung up and stuck and did some things. But at that point, we didn't take the approach that we're going to continue to try to run it without, things working correctly. We actually sent the tool back to the tool shop. They sent it back within about 12 hours, and then we put the process in off the process simulation and matched the process simulation at about 92%, which was pretty impressive. So in this case, just like we did here, we had a lot of people on the team. We made it happen. We came back and verified it. The interesting thing about it is that product went into production later that afternoon after we validated that entire process, and now they're running it on a daily basis with their technical staff understanding how to run the process, and they run it in 3 different machines. So that's an example of how we optimized using these approaches. Keep in mind, 90% all of this activity in the example that I just gave you was completed up front. Only 10% of the activity actually happened at the end of the day, which is really nice because it doesn't create chaos and confusion on the floor for everybody. Everybody knows their role. They know what they have to do, and if they have to ask questions, they do that to set themselves up for success. The big thing is also communication at every stage of the process. We want to continue to improve and practice and hone our skills. One of the ways that we do this is utilizing the successful strategies of the tool launch process and evaluate it for accuracy. And also in this communication process, we have stage gate reviews to understand what our risks are during the entire process. Maybe there's some people in the organization necessarily don't believe in simulation and risk assessment, but the interesting thing about that is if you're communicating it and you're having your reviews, you can always come back and challenge those things and go back and validate that information. Okay. So at the end of the day, what is required to make a part? First of all, I got to have a product design. Secondly, I got to have the materials. The third thing is I need to relate that shape as the plastic sees it through a simulation process or some kind of manual risk assessment process. Okay? I want to take my simulation or my risk assessment to the real world. All right? And this is where I use the simulation data based on my real limitations of my molding machines across the span of molding machines that I utilize, and then I relate that back to a real world setup developed with a universal setup at the end of the day. We're having really good confidence with process simulations, using all the information we have from the machines and converting the data. The thing that I think is really outstanding about it in this particular case was the customer had went through the process of training their technicians on the floor to a certain level, and we really hit the mark because we took that translated simulation data and actually just handed it right to the technician, and they took off and ran with it.